Geometric Optics, Chapter 36.
The eyes of the Earth were ready to behold the origins of the Big Bang. Who could have thought that this dream come true would soon become astronomy's worst nightmare? Almost immediately, the solar panels caused problems. Every 45 minutes, Hubble moved from sunlight to darkness, with an abrupt temperature shift of hundreds of degrees. The sharp temperature changes caused the arrays to contract or expand, shaking the delicate machine for several minutes. Hubble had a bad case of the jitters, and no way to get rid of them. Tests over the next few weeks revealed an even more puzzling problem. Data from the 94-inch mirror simply didn't make sense. It seemed to indicate that the mirror could not focus. As the evidence mounted, no one was eager to confront the possibility of a major malfunction.
The primary contractor who had built the mirror and the telescope, and who was nominally in charge of helping to set up and align the optics, was saying in this period that there wasn't a problem. So I was on the one hand saying there was a problem. The official contractor on the other hand was saying there wasn't a problem.
And then all at once, the problem was too obvious to deny. A mistake in the primary mirror, an optical error 1/40th of the thickness of a human hair, had left Hubble seriously flawed. The astronomical community was devastated.
It was finally in late June that the final data came in, and we couldn't deny it. And it was just a crushing blow. I mean, I remember getting a call on a Sunday afternoon, and I was crushed.
The mirror disaster was immediately followed by a public relations fiasco. The press and public savaged NASA for its apparent hubris and incompetence. Coming just 4 years after the Space Shuttle Challenger tragedy, Hubble's plight made many wonder if NASA could do anything right. The summer of 1990 was filled with scathing editorials and brutal cartoons. The most complex scientific instrument ever built had become a national joke.
So, how did they fix the problem? Here's a famous painting for you from Monet. What's wrong with this painting? Take a look at it, study it, take all the time you need. I'll give you guys 2 more seconds. Time's up. We'll get back to it later. This person looks inverted. What caused the inversion? Here's a magnifying mirror. So how does the image become magnified? These are parabolic mirrors as opposed to spherical mirrors. Why use parabolic mirrors? The whole idea is to actually focus the light onto this pipe in the middle, and then they have oil in the middle, so just heat it up and then turn it into steam at some point by the time it gets to water. So, and then rising steam is going to turn to turbines, so we'll end up getting electricity out of it. So why use parabolic mirrors instead of spherical mirrors? It looks smaller at this mirror, so the question is why? How does a mirror make it look smaller?
Here's a dude with way more than enough free time on his hands.
How do we capture reality in a smaller form using cameras?
It's hard to imagine what an astonishing magic trick motion pictures must have first appeared to be. A moving painting in light, telling the stories of people nothing like us and just like us. A diversion from the cares of daily life.
It wasn't until B.W. Griffith in the second decade of the century that people suddenly began to recognize that this was a new art.
Beyond the fact that it's an art form, equivalent to that of theater, equivalent to that of painting and music, it is the great documentarian of all peoples. Moving film has made possible a historical record which hitherto never existed. If we had had film in the days of ancient Greece, my God, what a sense of history we could have. Motion pictures have changed our perception of how other people live, think, feel, act, and behave.
We all modeled ourselves to some degree on people in the movies. I hope to become something like William Powell, Robert Montgomery, or Rex Harrison, urbane, graceful, witty. But I failed in that.
Take a deep breath when I say.
But in addition, they were very entertaining. Movies are the distinctive art of the 20th century.
How do we take small images and magnify them? Like the way we magnify movies using projectors. Moving forward, how does something small become magnified? Something becomes magnified using a magnifying glass. Or something big can be made smaller by using a diverging lens.
Sometimes when the full moon rises in the sky, it appears much larger near the horizon than it does when it's positioned higher in the sky. Some observers judge the moon to be as much as 50 to 75% larger when it first appears. But is the full moon really larger when it's near the horizon?
What do you think? It looks larger, doesn't mean that it is. Or does this side change as it starts to move from the horizon to the zenith? All right, now we will once again go over the same concepts as we did before, and this time we will superimpose mathematics on top of it. Plane mirrors. So laws of geometric optics is what we are interested in. Law of reflection is the first one on the list. Angle of incidence is going to be the same as angle of reflection, and that's it. We discussed the reasoning of it during the previous chapter, so we'll just go forward. All right, so plane mirror is the easiest one. A couple of things we will need to know. You got the object, incident ray, the reflected ray reflects into your eye. Angle of incidence is the same as the angle of reflection. And behind the mirror, the image is going to form. All right, so this is object, this is real. The image is going to be behind the mirror. It's going to be virtual. This is known as, anything that happens behind the mirror is known as the virtual image. If you see the image before the mirror, it's known as real. If it's behind the mirror, it's going to be virtual. So you got the object distance, the image distance. All right, so what's missing here is you have to look at it from the perspective of the person. The person is standing right in front of her, and the mirror is a flat mirror right on the wall. Number one, you're not going to be able to see her back. Number two, you're not going to be able to see your face. There are other aberrations. I'm not going to focus on those. Just focus on these 4 bottles, which is fine. Notice that there's a 5th bottle here. This bottle is moved to the forward. Here it's actually moved to the back. Okay, so Monet, whenever he's doing his painting, decided to completely ignore the laws of reflection. So what do we know about the plane mirror? It's form an image, so it's going to be upright, and it's going to be virtual. It's not going to be real. So the best answer is going to be B.
Sometimes when the full moon rises in the sky, it appears much larger near the horizon than it does when it's positioned higher in the sky. Some observers judge the moon to be as much as 50 to 75% larger when it first appears.
I'm not sure why we're repeating this, but let's go forward in this place. All right, so images formed by refraction. Reflection is what we are focusing on. Let's focus on the spherical mirrors. Number one, you have a spherical mirror. Okay, so both sides will be reflective in this case. Just grab a portion of it, a piece of it. All right, so internal side is going to give us a concave mirror. The outside is going to give us a convex mirror. So both sides will be reflective in essence. All right, so let's focus on the concave mirrors first. So you got the incoming rays. I noticed that all of them are parallel to each other. And then we have the optical axis. It's going to be right in the middle. And these parallel incoming rays, the incident rays, upon reflection, they will converge to a point. This point is called the focal point of convergence. C actually represents the center of curvature. Center of curvature is going to be right at the center, and the focal point is going to be right in between the surface as well as the point. The point of this is going to be the center. I just couldn't figure out what to say. All right, so this is the radius of curvature that you're looking at. So if this is the focal length, the radius of curvature is going to be located twice the focal length. That's what it means. Using laser beams, you can actually see that the reflected rays are converging to a point. This is the focus, the focal point of convergence. So this becomes the focal point, and then you got the radius of curvature. All right, so if the radius of curvature of a concave mirror is R, the focal length is going to be half that distance. So C has to be the right answer. Okay, so regarding concave mirrors, we will have some rules that we will get to follow. If you know the object, we'll check to see where the image forms, the size of the image and whatnot. So we will draw some ray diagrams, and ray diagrams follow certain rules. All right, so this is rule number 1. So notice that the incident ray, which is parallel to the optical axis, upon reflection is going to go through the focal point. The ray that's going incident through the focal point upon reflection is going to go parallel to the optical axis. A ray, which is coincident with the radius of curvature, is going to get reflected upon itself. So these are rules that we will get to follow. Okay, so a light ray traveling parallel to a concave mirror's axis, optical axis, strikes the mirror surface near its midpoint. After refraction, what do we expect? Okay, so what do we know? If that's the case, this is the one that we're looking at. So it's moving parallel to the optical axis. After refraction, it's going to go through the focal point. So it should go through the focal point. So D has to be the right answer. So the light arriving at a concave mirror on a path through the center of curvature. This is the one we're looking at. It's on a path that goes through the center of curvature. It's going to get reflected onto itself. So the best answer back parallel to the axis. So it's going to end up getting reflected back onto itself. All right, so focal point is kind of easy to figure out. So you need to have a distant object. This would have been a nice lab experiment. And further away the object is, the more the rays are going to be parallel to each other. So the reflected rays are going to converge to a point. So that becomes the focal point. All right. Notice that the person looks upside down or inverted. So the question is why. So let's just come up with some explanations using the ray diagrams. We got 3 rules that we'll do. All right. So this is the focal point. This is the radius of curvature. Let's place the person outside of the radius of curvature. And then by using the ray rules, let's find the point of convergence for the reflected rays. So this is, upon reflection is going to go through the focal point. This is rule number 1. The second ray going through the radius of curvature is going to get reflected onto itself. That's it. This is our point of convergence for the reflected rays. So that's where the image is going to form. Okay, so one thing that we know about the image, number 1, is inverted. It's inverted. It's going to be smaller, and it's appearing in front of the mirror. What that means, it's going to be a real image. So we got conclusions. Conclusion number 1. It's going to be real. Obviously, it's going to be inverted, and also it's going to be smaller. So that's what we expect to see. Likewise, you got the light source in this case. This is the candle, and here they end up using 3 of the rules. So the first one gets reflected, goes through the focal point. The second one is going through the radius of curvature, gets reflected onto itself, and the third one is going through the focal point, gets reflected, and goes parallel to the optical axis. So the point of convergence is here. So the candle would look like this. Here's the original candle, and notice that the reflected candle looks real. It appears in front of it. It's going to be inverted, and it's going to be small, slightly smaller than the previous one, just like this person is. All right, so here's the second case. Notice that this time the object is located between the radius of curvature and the focal point. Let's check to see where the image forms and the nature of the image. Our ray diagram rule number 1. And notice that the reflected ray is going to go through the focal point. And then the ray that goes through the focal point is going to get, upon reflection, is going to go parallel to the optical axis. All right, so our point of convergence here. So the image is going to be located here. Notice that the image is in front of the mirror. It's going to be inverted. It's going to be larger. So the conclusion is, image is going to be real. It's going to be larger, and it's also going to be inverted. All right, so this is the same case. This time we get to use 3 ray diagrams. So the point of convergence here. So the image is going to be inverted. It's going to be larger. All right, so the image produced by the mirror is going to be located outside of the radius of curvature. And so the best answer is going to be up past the center of curvature. A has to be the right answer. Case number 3. All right, so the object is located outside. The image is going to form here. So this will be a derivation. Lowercase f is going to represent focal length. P is going to represent the object distance. Q is going to represent the image distance with respect to the center of the mirror. This is the formula that's going to tie the focal length to the object as well as the image distances. We will also need an expression for magnification. H is the object height. H1 is going to be the image height. For magnification, we will use M. So M is going to be the ratio of the image height to the object height, which can also be expressed in terms of the image distance to the object distance. And notice that there's a negative in front of the ratio. Let's take a look at this problem.